right, chapter 2. First, we're looking at the differences between physical properties and changes and chemical properties and changes. So it's important to understand that physical properties are things that you can see or measure, and these are the kinds of things that you're observing in lab. Things like that would be color, size, shape, temperature. And changes are, physical changes are any changes in those types of properties. And the key thing about physical changes is that they can be easily reversed. Things like heating, cooling, melting, freezing, boiling, dissolving, bending, evaporating. All of these things we can undo rather easily. Whereas if we look at chemical properties and changes, they cannot be reversed very easily. And that's because chemical changes are changes that actually change your substance. Okay, so chemical properties are things that predict the reactivity of substances. We can really only observe those when a substance can be changed into another substance. For example, iron nails will rust if we leave them outside because the iron is reacting with oxygen to create iron oxide. So that's a change in your substance. It's no longer just iron and elemental oxygen. Now it's iron oxide. So it's a different substance and it behaves a different way. And it's very difficult then to rearrange the atoms again to get them back to their original starting point. And so chemical changes are those that are caused by chemical reactions. Okay, another thing that we need to understand the terms for would be macroscopic versus microscopic. Macro meaning large, right, and micro meaning very small. Scope having to do with things that are seen. So macroscopic is things that we can see and observe with the naked eye, and microscopic refers to things that cannot be observed directly. Atoms, which we talk about a lot in chemistry, are on the microscopic scale. So even though we can't see them, we do understand how they behave, and we can observe on a macroscopic scale evidence of those behaviors. So all substances are matter, and all matter is composed of atoms. And specifically, each different type of atom is called an element. Okay, and elements then are those fundamental pure substances from which all matter is made. And we have specific types of atoms, and we can categorize them, and we understand that all atoms of the same element will be similar to each other, and they'll behave the same way. We look at atoms first because they're the single building blocks that make up matter. Everything is made of atoms, and if we understand how those atoms can combine, then we understand the chemistry involved. We can look at different substances that are made, and we can predict how they behave. And atoms themselves are made from 3 different subatomic particles, and you had practiced building these when you were doing lab 5A. We know that atoms are made from protons, neutrons, and electrons, and we also know that protons and neutrons have an equal mass to each other. And rather than go into what that specific mass is, it's just easier to call it 1. And so we designate that amount of mass as 1 atomic mass unit, and we abbreviate that as an AMU. So protons and neutrons have a mass of 1 AMU. Whereas it takes 1,800 electrons to have the same mass as 1 proton or 1 neutron. So electrons have 1/1800th of an atomic mass unit as their mass. Charges on protons is a +1, charges on neutrons is neutral or 0, and charge on an electron is a -1. Now, if we add up the mass for an example being carbon, a carbon-12 atom, we know that it has 6 protons, 6 neutrons, and 6 electrons. So we get 6 AMUs worth of protons, 6 AMUs worth of neutrons, and 6/1800ths of an AMU worth from the electrons. And when we add all that together, we get 12 and 6/1800ths atomic mass units, which is practically just 12. So it's easy to see how all of the mass really is contingent upon your numbers of protons and neutrons, and how the mass of an electron doesn't really affect your overall mass. Okay, so it's important to know that most of the mass in an atom is from the protons and neutrons. Very small amount is from the electrons, but again, that amount is so small that we can overlook it. It doesn't mean that there's no mass in an electron, it just means that it's small enough that it's negligible. If we arrange the elements based on similar properties and groupings, we end up with what we call the periodic table. And the periodic table helps us predict different ways that different elements will behave. Everything is organized based on specific categories, and it's important that you understand the organization on the periodic table. You will never have to memorize the periodic table, but you do have to understand how things are arranged and what that means for the elements that you're asked to describe. One thing we can tell from the periodic table very easily is whether an element is a metal or a non-metal, or somewhere in between. So metals have properties of being shiny and dense. They're really great conductors of heat and electricity. That's why all of our cookware is metal. That's why our wiring is copper. They're usually solids at room temperature, and the elements on the left of the periodic table are generally metals. Non-metals, on the other hand, are dull. They're very poor conductors. They can be solid or gas at room temperature, and they reside on the right side of the periodic table. Now, there are a few very special elements that have some properties that would categorize them as metals, and some properties that would also categorize them as non-metal. And so they're kind of somewhere in between, and we call them semi-metals or metalloids. And you need to be okay with seeing either word used to describe those metals, those elements. They're not metals. They're semi-metals or metalloids. If you look at the periodic table, you'll notice that there is a staircase. Okay, on this periodic table, you can see that dark bolded line a little bit. If you look at where the lavender shaded metalloids are, okay, there's that dark thick line starting right at element 5, boron, and that zigzaggy line goes all the way down to in between 84 and 85. And any element that touches that line can be categorized as a metalloid. Now on this table it shows that aluminum and polonium are both metals, not metalloids, even though they touch that line. You would never be asked about those two elements specifically because there's some debate in different textbooks as to what to categorize them. So just remember that anything that's touching that bold line is a semi-metal or a metalloid. Okay, and as you can tell, everything to the left and below that those semi-metals are metals, except for element number 1, which is hydrogen. And we'll talk later about why hydrogen is placed on the periodic table where it is, but it is a non-metal even though it's on the left side. And then, of course, everything to the right of your semi-metals or metalloids are called non-metals. If we are to look at the periodic table, the way it's set up, you need to be able to read it. In the middle of the box is your element symbol. It's an abbreviation for the element name, so you don't have to write it all out. We just use the symbols, and it's typically centered in the box. Elements that have 2 letters in their element name, we always capitalize the first one and use a lowercase letter for the second one, and that's so that when we write chemical formulas, we can tell where new elements start, okay? At the top of the box is the atomic number, and that's what gives us the element identification. It is the number of protons that determines how an atom will behave, and thus that's what determines what element we have. If we read the periodic table, we've been using terms like rows and columns so far, but it's important that we start to switch to what the actual names are. Okay, so a row is actually called a period, and a column, which moves up and down, is called a group or sometimes a family, depending on which column it is. The number at the bottom of each element box is called the atomic mass, and remember it's equal to the number of protons plus the number of neutrons. It is a decimal number, but when we use it in calculations, it's okay to round it to the nearest whole number. which brings us to the mole. Okay, the mole is just a word that describes a specific number. Okay, so if a pair is equal to 2 and a dozen is equal to 12, and we've already used an atomic mass unit to equal the mass of one proton. So 1 AMU is actually equal to 1.66 times 10 to the negative 24th grams. We can also use this number mole. Okay, if we wanted to have our atomic mass in grams, for example, carbon, element number 6, has an atomic mass of 12. Now, if we wanted, instead of AMUs, if we wanted to have 12 grams of carbon, we would need a mole of carbon-12 atoms. Okay, and that's something that was calculated and developed a long time ago. So a mole just refers to how many atoms we need of carbon-12 to be equal to the molar mass in grams. Okay, and so it's carbon-12 that the mole is based on, but we can extrapolate that number to use for any element. Okay, and mole, which is also sometimes called Avogadro's number, named after a mathematician, not after the guy that came up with the mole. And that is equal to 602 followed by 21 zeros. And so we abbreviate that using scientific notation as 6.02 times 10 to the 23rd. So it takes 6.02 times 10 to the 23rd atoms of carbon to be equal to 12 grams. And so if we're going to write that in instead of in atomic mass units, we want to use grams per mole. For example, in carbon, we know that if we were to have a mole of atoms, we'd have 12.011 grams. Or we can use that as 12.011 grams per mole. And we can see how now this creates a nice little conversion factor that we can be using in further calculations. So let's go back and look at some of this vocabulary again. One atom is a single particle building block. Now, if we have more than one atom bonded together, we have what's called a molecule. An element is a single type of atom, and it can be one single atom, or it can be molecules that are made from a single type of atom. For example, you can have one oxygen atom, or you can have two oxygen atoms bonded together. It's all still elements because you only have one type of atom. A compound, then, is when you have more than one element bonded together, and most matter that we have is in the form of compounds. We have millions of substances that are made from 92 elements. The elements numbered 1 through 92, uranium, can be found naturally, but 93 and above are created synthetically in labs. So everything we have that is not synthetic, right, is made of differing combinations of elements 1 through 92. All right, so the chemical formula tells us which elements are present and how many atoms we have of each. For example, water is H2O, and that tells us we have 2 hydrogen atoms and 1 oxygen atom. Let's look at sodium bicarbonate or baking soda. Okay, we have NaHCO3. There are 3 oxygen atoms, 1 carbon atom, 1 hydrogen atom, and 1 sodium atom. All of that we can tell from the chemical formula. It doesn't tell us the structure though. Okay, so atoms can be bonded in different ways. That makes molecules. Molecules have one chemical formula, but if we rearrange the atoms in different ways, we can have different structures. So here we see 3 different examples of C9H8O4. They all have the same chemical formula, but we can tell that the atoms are not bonded in the same ways, and it makes 3 completely different compounds. Ionic compounds are when we've got ions that are attracted to each other to form a compound. An ion is simply an atom that has lost or gained electrons. It has a charge, either positive or negative, and we can see that the positives and negatives are attracted to each other. And they will have charges based on how many electrons have been gained, which would make it more negative, or lost, which would make it more positive. Okay, so ionic compounds are alternating ions of positives and negatives that are each attracted to each other, like salt, sodium chloride. The formula mass you have practiced calculating. It's also called the molar mass, and it's where we calculate the mass in grams of 1 mole of molecules for any particular substance. We do that just by adding all of the atomic masses. And here was the homework that was assigned. Hopefully you're done.